So our first talk is with Richard Harding. He'll talk about the nexus of land, food, energy, and water, including water management in global scale models. So Richard's a senior research fellow with the Center for Ecology and Hydrology in the UK, and he's been gracing us with his presence for the last few days on the CCRN meeting as well. So, and decades, that's true. I've known Richard a long time. So welcome, Richard, and thank you very much.
Hello, good afternoon, and thank you for this opportunity to talk to you. Can we get my presentation up? Okay, good. Yes, I'm not sure if I'm going to cover the whole of food, land, water, and energy and management in global models in 15 minutes. So I'll just give a few thoughts that I have. I've kicked off with this, this graphic really to illustrate what might happen in the future. This is some simulations using a global hydrological model called water gap, showing a very crude index of water scarcity. It's the basins where, in the red is the basins where about half or more of water is already used for water withdrawals, and an estimate of what might happen in the future, and as you can see, there's a lot more red. In fact, let's get this going if it works. The number of water basins likely to experience severe water stress is projected to increase by, well, over 40% by the end of the century. This is for two reasons. It's from increasing population as well as climate change. And it's just one of those estimates. I'll just step back and talk a little bit about food and population. I mean, we all know population is rising. It'll get up to 9.5 billion by 2050 and 11.5 billion by 2100. And also, very interestingly, the proportion of urban populations is going to increase. It's already more than half. This is, as we discussed a little bit this morning, is going to put huge pressures on water supplies to our mega cities and our urban areas, as well as having to still supply water for agriculture. And the number of undernourished people, we've done very well actually in the last few decades. Actually, going before this, I couldn't find it quite graphic. I mean, in 1990 there was over 1 billion people who were undernourished by this index. In 2000 it was 900,000. It actually dropped quite substantially down through the early 2000s, which is a sort of a triumph to development, really. And we're now down to less than 10%, or down to 10% of the population. Still too much, and still not quite getting there with our Millennium Development Goals and such like, but a great improvement. What has happened, and I was quite interested to see the latest FAO report, in fact it's ticked up in 2015 to 2016, which is the most recent estimates. We don't know, I guess, whether this is just a little bit of variability or whether actually it's the beginning of a trend going very much the wrong way. And that's something which we need to look at. One little interesting diagram, and I'm well outside my comfort zone here, but I thought I'd put it up because it looked interesting to me, is the number of conflicts in the world. And there's also this fact, is of this 800 odd million people who are undernourished, the majority, or well over half of these, are people in countries which have conflicts. And the number of conflicts, we can could argue, I guess, a lot about how you define all this stuff, but seems to have been running along, or even going down slightly through preceding decades, but has shown a sharp rise in the last 5 years. And I guess, well, we all see the news and hear where those sort of things go. And certainly the prevalence of undernourishment is much higher in countries where there's conflicts. But, in fact, it's also likely to be due to, there also is an important effect of climate shocks or pressures, and certainly the most recent El Nino caused substantial droughts and occasional floods right across the world and had a contributory factor to food production and malnourishment, and possibly, and it's a more tenuous link to the development of conflicts. So going back to where I'm feeling a bit safer now, back to water use. This has been rising. A lot of information here. It's been rising with global population. It's probably not been quite rising at quite the rate of population, which is perhaps good, because we're perhaps using, as we heard this morning, in many areas of the world, using water more efficiently. About 3/4, 70% of water withdrawals are used for agriculture, but an increasing amount is used for domestic use and industrial use. And this comes back to some of the pressures that we're going to see with our increasingly urbanized society. But, you know, this can't continue forever. Or maybe it can. We've got lots of, we total up the total land precipitation. It's a huge number, 100+ thousand cubic kilometers, and it's difficult enough to conceive of a cubic kilometre, let alone 1,000. Anyway, it's an awful lot. Of about half runs off and so is potentially available. We store quite a substantial amount of that and actually use quite a small amount for irrigation. It's still a massive amount. These are all per year, by the way. What is worrying, and this is a model calculation made a few years ago, is that a substantial amount of that is being extracted unsustainably for groundwater. And we have seen, and we may see some from GRACE results later, or some. There are many areas in the world where we can see groundwater levels dropping. But behind these big numbers is very much a regional problems, and we can see areas in red here where we have, well, it says it, a substantial anthropogenic impact on average river discharge, and we see areas, again, in this band of highly populated, semi-arid regions where we're really using well over half our river resources already for irrigation, for water use, for industry and such like. So these numbers really hide massive potential problems for the future. And of course, they have other impacts. It's a bit of a diversion, this. But if we look at the measured sea level of 2 millimeters rise a year and look at the thermal expansion and the melting of glaciers and ice sheets, it doesn't quite explain the measured sea level rise. And this is, again, a model output, but it's likely to be dewatering of the groundwater. Makes a substantial input into the sea level rise we see out there. And of course, sea level rise is going to be one of the major problems for some of our coastal cities in the future. So we were asked about where some of the big advances have been, and the global data sets, and I've shown you some of the analysis from them, the progress on this has been really substantial in the last few years, or last few decades, I guess. I mean, we've had really good data centers and data sets for precipitation and satellite stuff. We've got the gridded global data coming out of the climate and weather forecasting centers. We've developed some really good land surface maps and stuff, and this is only part of it. And also some really good data to validate and calibrate some of our models here. Sorry, a load of alphabet soup of acronyms, but some of you will recognize this. And we can put this sort of stuff together to make our best estimates of hydrology across the globe. And these are just some of the diagrams that come out of that. We can also start looking into the future. This is an analysis that came out of the ICIMIP initiative, where we took, these are estimates of water scarcity, potential water scarcity for different warming above the average, and what we've got here is 5 climate models and a whole range of global hydrology models. And this is the percent of the world's population with less than 500 cubic meters of water a year. And that's for everything, and that's quite down in the water scarcity area. And I think there's 2 messages to take off some of this analysis. There's a lot, and you can always go and read the paper. But one is that as global warming continues, the number of people living in these water-scarce areas is increasing. There are population increases in this analysis as well. But the other thing we need to look at is some of the massive variation between our global hydrology models, and we certainly have massive problems with those, which we need more data and more analysis of, so that we've got more confidence in these. Although, having said that, even though there's a huge spread, there's still a message coming out from here. Drought, I think I've mentioned before, it's this variability, and people have been a bit bored with me talking about this in the last couple of days. Droughts and the prevalence of droughts are what will get us the change in mean and average conditions perhaps we can deal with. But again, an analysis from the ICIMIP ensemble of models suggests that droughts are likely to increase again, well, over an awful lot of the world, actually. The drought duration is likely to increase quite substantially in the next 100 years. These are droughts defined by river flows, and I think they're from the 95th percentile. I put this one in, and again, it comes from the ICIMIP analysis, and I don't want to talk too much about it because it deserves a whole lecture. But what we've got here is essentially an analysis of droughts in the future for all these RCPs using the different hydrology models from, there's a Japanese one here, German, and UK, Vic is in there. And you can see that most of the models actually show a movement to the right there, which means that there's going to be more drought. Except for one model, which is my personal model. Well, it's not my personal, but it's the UK model, Joules. And the difference with this one is that it has carbon dioxide fertilization. So stomata shut when the carbon dioxide is, well, they don't open as much because the stomatal opening is controlled by the carbon dioxide. So as carbon dioxide goes up, actually the vegetation uses less water, and so actually you get even a slight decrease in future droughts. And this just illustrates, I'm not necessarily saying which is right, but it just illustrates that if you change the physics in these models, you can make massive differences to future projections. So just to come back to my nexus, and there's lots and lots of nexuses, but to summarize what I was talking about earlier, natural disasters can certainly cause food shortages, are likely to cause conflict, and there's lots of anecdotal evidence, and it was mentioned, I think, earlier today that maybe some of the problems that we had in the Arab Spring and such like were to do with some droughts and changes in climate. The important thing, I think, is we can't do very much about some of this, but we can improve resilience of communities and water supply systems. And if there's one thing that as a hydrological community can do, we can do that. And one thing that we are doing, and this is just a few examples, is to start producing real-time analyses of current drought position. We can take it forward with the climate, with the weather forecasting models to look into the future a little bit and produce these continental scales or even global scales, projections and estimations, which should be very useful for us to be able to both anticipate possible problems and provide some solutions, notwithstanding the sort of governance problems that we heard about earlier. But hey, you know, we can only do what we can do here. A new kid on the block, which I thought I'd mention because CH is involved in this, is a new WMO-sponsored system called Hydro SOS, and I'm hoping you'll hear more about this in the future as it gets off the ground, but it's recently been agreed by WMO. It's going to do what some of these other systems do, which is run global hydrology models, but it's also going to link to regional pilots, regional studies, and regional climate and hydrological services to provide, one hopes, a good service and some improvement in resilience of systems. So I'll virtually finish there. Hopefully avoided the dreaded hockey stick. And just to say, well, yeah, water is a major constraint and it will continue to be a major constraint. And analyses of future food, which I haven't talked about much, all suggest that future food needs can be supplied, but only with very careful and sustainable use of water and land. Variability is important, and that is going to be increasingly important. And certainly the global information that we've started to develop, I think, has an important role here to help us manage our freshwater systems and help societies adapt. Thank you.
So we'll allow a bit of time for questions if anybody has any questions for Richard. Stand up, please, and shout.
Between those?
Yes, I mean, it's quite interesting. Some of the results I'm showing there have taken the climate model outputs, the temperature, humidities and such like, offline and then run them through hydrological models. And some of those hydrological models have been calibrated. For example, water gap is calibrated on, I forget what it is, 2,000 basins across the world. So some of those do contain calibration. Calibration is dangerous, particularly going into the future, because if we really want to do this properly, we need to change, when we want to change things like vegetation cover, management practices, and all those other catchment characteristics which are swept up in the calibration. I'm not going to completely answer your question because I don't know whether that sort of study has really been done. You could look at scenarios to see whether catchment characteristics might change enough. Although broadly, the uncalibrated models look the same in terms of the way they work than the calibrated models. So.
Okay, any more questions? Great. Thanks very much, Richard. That was great.